based off of the design of an experiment. So the vocabulary, which I asked you to look over before tonight, but it's like I said, it's just familiarizing yourself with the words. It's a lot of it is kind of vague and sort of out there. So the first term there is the null hypothesis. Either a statement that's being tested or some understood or accepted value for the population parameter, also known as the status quo. Right. The last part of that, where it says the only sign used here is equals, that part wouldn't really make much sense right now, but it will once we get into an example. Right. The alternative hypothesis, which we're going to use a symbol HA for, H with a subscript of A, as opposed to the H with a subscript of 1. The reason why I put both is because different textbooks use different notation, so I wanted to make sure you had access to both. All right. Fruta. Okay, I'll add it to the list. Organic garlic mint. Okay. All right, so if we say that a hypothesis involves an equality, so if I say that, here's my claim, I think that the average number of people who, I don't know, experience a serious cough, I don't know, is 12. If you have a small population, a population of, let's say, 50 people, and the average number of people that at any one time would experience, actually that'd be kind of high, 12%. Let's say 100 people in the population, and you want to say the average number of people that experience a cough is 12, that would be the null hypothesis, because that's it's an equal sign, right? The alternative would be that it would be in some way not equal to that. Right? So there's 3 ways you can be not equal to a number. You could be more than, less than, or simply not equal. In which case you would be indicating that you didn't really have an idea of whether it's more or less. You just know that it's not the right number, right? So if I said, well, let's say the population size was 50, and I said that on average 12 people out of every 50 will experience a serious cough at any given time, you might say, I don't know if it's more than that or less than that. I just know that it's not that. Right? That's the case of the not equal. All right. Sometimes you have evidence or statistical information to indicate or to allow you to draw a conclusion that it is in fact more than that given number, or in fact less than that given number, but that doesn't always play out. Right? That's why in the lecture last time, I was saying that, when you do an exploratory data analysis, you kind of go into the situation, with an open mind. I don't know what the effect is of a particular variable. I just know that there is one. But you go in thinking, all right, there's got to be something going on here. I just don't know what it is. All right. So that kind of leads you to the alternative hypothesis. But it's all going to be based off of the framework in a particular problem. The significance level alpha, the Greek letter alpha, is the cutoff probability for rejecting a true null hypothesis. That sentence right there is kind of the crux of the whole thing, but it rightly so, shouldn't make too much sense right now, right? Because you look at it and say, well, that's great. The cutoff probability for rejecting a true null hypothesis. First off, so many things wrong there. Why would we consider rejecting something that's true, right? So let me just clarify that part. We want this probability to be very, very small. All right. The most common values for alpha are 0.10, 0.05, and 0.01, with 0.05 being the most popular. All right, and you can see the little breakdown there. 0.10 is rarely used as part of an experimental study. 0.05 is most common because it assumes that an error in an experiment can occur about 1 in 20 times, which is, that never really sat right with me, but that's actually the genesis of it. What happened was early on, when all this stuff was being formulated, when people were making decisions on how, appropriate statistical processes would go, somebody just kind of made the call and said, 1 in 20. That's how often I make a mistake. That's how often I screw something up. 1 out of every 20 times. I mean, it's a little bit more complicated than that. I'm just kind of tongue in cheek about it, but it's not too far off from that. It's based off of experience. It's saying that historically, about 1 in 20 times, an error in an experiment would occur. So they just kind of went with that. Now, I wouldn't like that to be the case, but it kind of also fits with a lot of the concepts that we have in probability, and that is that if we talk about a probability that occurs less than 5% of the time, we consider that to be unusual. So if an event is considered to be unusual, then it's probably either because of an error in the experiment or because of some significant effect going on. So if I tell you that there's some outcome that's occurring, and it's so unlikely, it's like, well, there's no way that can be occurring, but yet it is, then you wouldn't think that it's occurring due to nature. You would think that it's occurring due to some sort of outside influence. That's what a statistical inference test is telling us, whether or not there's some sort of external influence going on, right? And so if we can draw that conclusion, or if we can allow for that conclusion to occur, then we're strengthening the relationships that exist between variables, but we're also allowing for what's known as statistical significance, right? And it's kind of weird because you see this little statement here, where significance in a hypothesis test does not always mean that there's a strong effect, only that there's strong evidence of some effect of some imposed treatment. Right? And what that's telling us is that there is a relationship that exists. It just might not be a strong relationship. All right. So going back to the alternative hypotheses, I have a greater than, a less than, and not equal. The result of a hypothesis test could be that the hypothesis test supports the alternative hypothesis of a greater than. So my little simplistic example of, out of 50 people, I think that 12 out of those 50 people will experience serious coughs. You might say, no, I think it's more than that. I think it's less than that. Let's say you think it's more than that, and the hypothesis test supports your conclusion. All you get from the hypothesis test is that it is more than the number 12. Just because it passed the hypothesis test doesn't mean that it's a lot more than the number 12. It just means that it's more than the number 12. That could be 12.01 then. Could be 12.5. Could be 13. Or it could be 48. So it's really just a question of, like the conclusion, because that's really what tends to be the case. Because when they say, like you listen to commercials and stuff like that, or you actually read a statistical analysis, they'll say at the 5% level, the results of this study support the conclusion, blah, blah, blah. And people walk away with the idea that, oh, it's more than 12. Oh, okay, so that means that the original claim was horribly wrong. Well, it might have only been slightly wrong, right? And also, the outcomes of the study will be dependent on the alpha value that's selected in the problem. Now that part is a little bit out of, like I'm speaking out of context here, so that it's not going to make sense just yet until you see an example, but it will. All right. We also have things like type 1 and type 2 errors. Type 1 is rejecting a true null hypothesis. Type 2 is accepting a false null hypothesis. Both of them are bad. If you reject something that's true, why would you reject something that's true? You wouldn't want to do that. Accept something that's false. If it's false, why would you accept that as being a fact? Right? But the one that's considered more egregious is more, oh boy. I have no idea. I just took a shot. Oh, look at that. I think I spelled it right. What do you know? Something went right tonight. So that was step 1. Step 2 is making sure I use the right word, and I just looked it up, so I know I did. Right, but it's kind of it's the perfect word. You know, I just Googled it just in case. Extraordinary in some bad way, glaring, flagrant, an egregious mistake, an egregious liar. You know, that's the meaning there. I mean, I honestly can't think of a better word to describe it. I mean, the other one is, I mean, I guess it could be egregious, but this one is more. This is more worser. It's so terrible. Yeah, it's because, and the reason why is the null hypothesis is typically related to the status quo. Right? So some long-standing rule or belief. If you're going to dismiss a long-standing rule or belief, you damn well better be right about it. Right? If you're going to accept a false claim, well, guess what? People do that all the time. Doesn't make it right, but people do it all the time. Now, if you're going to take a system and tear it down, you better be right about things. Right? So that's the idea here. Yeah. And so the alpha value can be thought of as the probability of making a type 1 error. The idea is that we want alpha to be as small as possible. So I want the probability of making this mistake to be unusual. I want it to be unusually small. I want it to be so small so that it's, I don't want to say negligible, but so small that if something is going on, that it's likely because of some outside influence. All right. So, oh, by the way, my little diagram here, this is the best I can do, but you get the idea. It's the bat signal. Like I said, best I got. But what it was is the idea that the lamp itself is supposed to be a sample, or at least in my mind. And the signal in the sky is the population. And this is the sample projecting onto the population. This hand-drawn diagram even is better than what I had there originally. All right, so sample projected onto the population. The thought process there is that if we could use information from our samples and just kind of broadcast it out into the entire population, would it still hold up? You know, would it still embody the same characteristics for the population that it does for the sample? A statistical hypothesis test, or also known as an inference test, will allow us to make that determination. If the information that you gleaned from a sample is going to hold up for the entire population, it'll come through this statistical process. Right? So that's the idea there. I'll take it as a typo. Oh, the diagram. I can easily modify it, at least by drawing the lines. It looks a little nicer. So, so if somebody needs some typo bonus, go for it. You know, like I said, I'm not feeling so hot, but that doesn't mean you can't submit a remind message for bonus credit, because I know there are lots and lots of people who have not gotten any bonus credit throughout the entire semester. It's almost to the point where I'm wondering, what are you waiting for? No, I'm wondering if maybe I didn't do a good job of explaining that whole process. Anytime I point out a typo in the, you know, during a lesson, during a class, you know, for example, take a look at this bad boy here. Look at that, the font difference on alternative hypothesis. It looks kind of nice for null hypothesis, it fits, but then it's kind of elevated for the notation, the H1 and HA. It's not quite, it's a little out of sorts there. Same thing with the alpha over here. This looks a little off, right? Those are typos, right? And anybody could submit typos at any time. And if you submit them, you get bonus credit. You get 1 point for every typo you submit, right? Yeah, there's another one over here. So it helps me improve my notes, and the reward for you is that you get some bonus credit. And so I know a bunch of people, and I don't want to blow up their spot here, because they've been cashing in all semester on those typo bonus points. Good for them. But you know, there's plenty to be had, so definitely take the opportunity to do so. I know some people have the tendency to say, well, you know, I'll take care of that at the end of the semester. If I don't need the bonus points, I'm not going to bother. But the issue with that is because it's first come, first serve. I think that's the key. If I talk too much, that's where it all falls apart. If you wait till the end of the semester because it's first come, first serve, then you'll find that you'll be submitting typos to me, and I'll be like, got that one too, got that one. You'll be 30 typos in, and I'll be like, yeah, keep going, because I got all those already. You know, so just to, you know, as they come along, through remind. Yeah, just send them. So the question was, how do you submit them? Guilty, very nice. How do you submit them? Yeah, just send a message on remind, and the message, all you'd have to say is on page, for example, this one, page 60, fix the diagram. Typo, fix the diagram. Page 60, typo, fix the the H1 HA. You know, and that's really it. And if you do that, then I take note of it, I update it in Blackboard, and everybody's happy. Right? So, and you can see like the notation here, the HO, it's just a little offline. You know, just find those instances. You don't even have to wait for me to say it, because you'll find it. You'll find those instances. All right. So oh, gotcha. Good question. Good point. Yeah. Oh. All right. So we're going to talk about the p-value approach. The p-value approach is a comparative value that we use when determining whether there's significance within a test. Right. So there's a couple of things that we have to do in order to come up with the p-value, but it's really not that crazy. I'm just wondering if that's the way I want to do it now. I'm just having second thoughts because we're using Desmos and not the TI calculator. We'll see. Yeah, all good stuff. So, well, anyway, the p-value is the probability that the null hypothesis is true. Right? So it's a simplistic way of stating it, but it's also it kind of drives at the point. The alpha is the cutoff. If the p-value is less than the alpha, then the probability of a true null hypothesis is unacceptably small, so we reject it. All right. So that's something to keep in mind. But I'm not 100% sure we're going to do it that way. I'm just still kind of thinking this through. I'm going to use this box. So I'll box this in because it may be an important concept, but we may actually kind of deviate from it. All right, so we're going to hop along. Like I said, we're going to focus on two hypothesis tests. One is the one population mean where sigma is unknown, and the other is the match pairs design. All right, so let me just get rid of all this stuff. So a lot of this stuff is referencing hypothesis tests that we would have talked about beforehand. What we're going to do is just kind of look and jump right down to this information here. You know what? I could still talk about it because it says the first test relied upon knowledge of Z tables. Okay, that's fine. It does. It's still true. We're just not doing that test. This test uses the student T distribution. What is that, you ask? Well, it's a distribution that was created by a statistician that wished to remain anonymous. So he chose the nom de plume student. So I always thought that that he didn't want to be cursed by statistics futures students throughout the ages. So he made this pen name student. You're like, you know what? I was one of you. So you can't hate me because I was also a student and never told his name. Actually, I researched it recently. Turned out that he worked for Guinness. He worked for the like the Guinness, and they had a law, like their own law, internal law, like their own policy that prohibited the use of their name in any publications that wasn't like directly produced by them, by the company. So what this individual wanted to do was he wanted to work with small samples and draw conclusions about those small samples as they applied to entire populations, which kind of makes sense. It's sort of like what we're talking about here. And so he wrote this beautiful paper describing the student T distribution, but he couldn't use his own name because then it would be tied to Guinness. And then, that was against their policy. They said, what, not going to happen. So he's like, I got to use the pen name. And then, of course, other people took credit for his work over time. But the original name of student T distribution stuck in honor of this individual. Right? So the T distribution involves values known as degrees of freedom. There's a number of values in a collection that may vary after certain restrictions have been imposed. It's kind of a weird thing to say, but I kind of look at it as like you have a control over a certain number of values in a data set, depending on the parameters that are given. It's really just a question of how many of those values do you have control over. So I gave this example here. Assume you have a sample set with 5 values whose mean is 45. Right? So we go right back to day 1 of the course, well, day 2. Not counting the introduction, but we talked about the mean. Let me actually get the mean symbol in there. The mean of a data set being equal to sum of all the values divided by the number of values in the set. All right. So in this case, we have a total of 5 values, and the mean is 45. So based off of that, we could say 45 is equal to the sum of X over 5. Now, when I cross multiply to solve for the sum of X, I get 225. That's just computational justification for saying, well, when you added up all the numbers before you divided by 5, the sum was 225. So you had a data set containing 5 values. if you wanted to find the mean, you would add them up and divide by 5. The number that it added to before you divided by 5 was 225, right? So if I wanted to, I can decide on any numbers that I want to be part of this set. 1, 2, 3, 4, 5, right? As long as they add to equal 225. All right. So let's say I want the first value to be, I don't know, 50. Then I would have 225 minus the 50 that I selected. It'd be $1.75. And let's say, just to kind of make the numbers as nice as I can make them as we go, say the next one is 75. So I could subtract off the 75. Now I'm down to 100. Let's say, and I'm just picking up these numbers off the top of my head. Any number that's less than 225 is gonna work. You could even get decimals involved if you want. All right. So the next one, let's say the next one is 30. So 100 minus 30. All right, so I'm down to 70, which is telling me that I have 70 to split between the remaining two values. And so let's say I decide that my next value is going to be a 10. So I knock off a 10 from this. That leaves me with a result of 60. But since that last value has to be the value that gets me to 225, then that last value must be a 60. The decisions that I made previously dictated what that last value would be. All right, so I have no choice but to make this number 60. Right, no choice in the situation. I had the choice over the first four values, but that last value I had no choice. And that's always how it plays out. If you know the mean and you know how many values there are in a data set, you will have control over all but one of those values in the data set. You can decide on whatever you want. That last one will be decided for you, right? So you have control. And let me just shrink this down a little bit. All but one of the values in the set. That's the same as saying n minus 1. All right, there's n values in the set, 5 in this case. Minus 1 gives you the 4 that you have control over. All right, that is known as the degrees of freedom. Which we very creatively abbreviate with a DF. Right. The differing degrees of freedom will dictate the shape of the distribution. I keep hitting sign up, I don't know. So you could have different distribution or different shapes of distributions depending on your n value. Right. So I can give you a quick illustration here because I took the time to make the appropriate diagram. And this is available to your, I hope it is, I don't know. If it's not, it will be. All right. So we have a t distribution corresponding with a lot of computations associated with it, but I'm just kind of cleaning it up so that it looks a little bit nicer. All right, so the n value will impact the shape of the distribution. All right, so if my n value is small, the graph, and it's kind of hard to do it this way, but if I make my step, let's see if making it 0.5 will do the job. Yeah, a little bit better. You can see well, you might have to suspend your disbelief a little bit, but for smaller values of n, the graph is short and wide. All right. It's generally bell-shaped, but the shape changes based off of the size of the sample. But eventually, as your sample size increases, it becomes more and more normal. All right. Normal as in a normal distribution. All right. Not normal as in ordinary. So if you have a sufficiently large sample size, typically n being greater than 30, then we can use the student t distribution as an approximation of the z distribution. Right? I can't make squiggly brackets anymore. If n is greater than 30, we can use the t distribution instead of the z distribution. All right. The benefit of that is that you kind of have one-stop shopping, because t distributions are very flexible when it comes to smaller sample sizes. They're functional in the sense that you don't have to know what the population standard deviation is in order to get a meaningful outcome using a t distribution. In order for you to use a z distribution, you know, all that central limit theorem stuff that we did, you would have to have the sigma value. What this is telling us is that we can get away with a sample standard deviation and a sample mean in order to draw conclusions about a population, which is good because that's probably all we're going to have anyway. Because if you think about it, the process that we use to find a population standard deviation would involve us first finding the population mean. So if we're trying to estimate what the population mean is, and we already know what the population standard deviation is, it's kind of a contradiction, because it's like, well, we already had to know what the population mean was in order to figure out what the population standard deviation was. So why are we trying to guess what the population mean is? That doesn't seem to make any sense, right? So this type of distribution allows us to use sample information, just like that bat signal, and project it out into the population. Right? So I'm going to walk you through a hypothesis test. I made like a little flow chart here that pretty much kind of gets you the whole way. That's the idea anyway. Whenever you, oh, the formatting's a little off. Yeah, just honestly, if you're in need of typo bonus, just go through my notes and just pick it apart. You know, anything that looks a little out of whack, I mean, I just want them to get better, you know? So anything that you can find that's like, you know what, this will make it better, then just go for it, you know? That's all I ever ask. So the assumptions for a hypothesis test are important because it's weird. In a hypothesis test, we call them assumptions, but the reality is they're more like criteria. They're conditions, criteria that need to be in place in order for you to use that hypothesis test to begin with. So if I'm testing a claim about a mean, and you only get that from the context of the problem, where sigma is unknown, first off, I would want my information to be collected, you know, the data, the sampling process to be collected using an appropriate sampling technique, right? With a simple random sample being the most appropriate, right? So, but I'll also amend this to say, or other appropriate sampling method. Because you could use a stratified sample, you could use a systematic sample, you use whatever you want as long as there's randomization involved. We also are saying that sigma is not known. We don't know the population standard deviation, so we're going to use S instead. Right? That opens the door for the t distribution. So we know that we have to use the t distribution. All of the hypothesis testing techniques that we're going to talk about in this course involve you either having a normal distribution or the n value is greater than 30. Right? When I say approximately a normal distribution, I'm saying that the population is normally distributed. That would have to be a given piece of information, right? Because we're trying to draw conclusions about the population, but there are some things that you can assume. You know, when you're talking about things that are in a historical context, where it's like just the way it's always been is that it's typically a normal distribution, so we can make that assumption. If not, then we want our sample size to be greater than 30. All right. So the first step in the process for conducting a hypothesis test is to state the null and alternative hypotheses. And the second step is to choose an alpha value. Typically, we go with a 0.05, but the default is whatever they tell you in the problem. Sometimes they don't tell you anything at all. If they don't tell you anything about the level of significance, then you just use 0.05. If they tell you, then you use whatever they tell you. All right. The third step is the p is less than alpha. So we'll deal with that when it comes up. And then we write an appropriate conclusion. And the best way that I've experienced to handle this part of it, that that allows the logic to be sound, is by following a template. Even though the grammar might be a little iffy, it follows the correct logic and therefore will be correct. Right? So that's the importance of following this templated response. Right? When it comes to a test, I'll give you this flow chart. So you'll have the ability to follow the appropriate framework. But let's dive into the example and see where it goes. All right, so time it takes for students who drive to school on a daily basis to exit the school from their 8th period class is high school question. Start their car and exit school grounds approximates a normal distribution. So that's one of our assumptions. On February 3rd, 2003, a teacher had nothing better to do, timed a sample of 45 student drivers. So I'm just going to jot that down. My n value is 45. And determine the mean. All right. So contextually, that's saying that the mean of this set of 47 drivers is 5.7 minutes. All right. So the idea is that it's going to take them a certain amount of time to get out of class. We're assuming the 8th period class is the last period of the day. Get in their cars and leave. All right, and exit school grounds. So I guess the minute they pass the main gate, they're officially off school grounds. And it turned out that it took, on average, for those 45 drivers, 5.7 minutes. All right, so that teacher must have had a keen eye at the time and a really awesome lawn chair in order to really be in a prime spot to see the students leave their class and make their way to their cars and then get off the grounds. So, but anyway, it's the mean of that sample, so that makes it a sample mean. So x bar is equal to 5.7. With a standard deviation of 2.1 minutes. So that standard deviation only applies to this sample. So that makes it a sample standard deviation, 2.1 minutes. They say use a 0.01 significance level to test a claim. We'll get to the test of the claim part in a second, but use a 0.01 significance level. All right, so they're flat out telling us that the alpha value is 0.01. To test the claim that the mean time it takes the students to go through the above routine is actually greater than 5 minutes. All right, so greater than 5 minutes. Specifically the mean time. Now, they're saying the mean time it takes students in general. Talking about a population. Remember the bat signal. We're trying to project from a small sample to a large population. All right. So what I want to know is what this says in terms of the population mean. You know, does that tell me that the mean is going to be more than 5 minutes, less than 5 minutes, equal to 5 minutes? Those are our different possibilities. So I can note all that stuff. I can say, because the key number here is 5 minutes. I could say mu is equal to 5 minutes. I could say mu is less than 5 minutes. I could say mu is greater than 5 minutes. And I could say mu is just simply not equal to 5 minutes. All of those things are possibilities. Right? What I want to do is choose the most relevant ones. If you look back to the possible null hypothesis, it's the one that involves an equal sign. There's no decision there. Out of all my different possibilities, the one that has an equal sign, that's going right here. The alternative could be any of the other three. But since the question is saying that they want it to be greater than 5 minutes, I would select the one that has a greater than symbol. Right? It just seems to make sense. Why would I choose a different inequality than the one that's being asked in the problem? All right, so out of all those possibilities, I selected the ones that are relevant to the hypothesis test. I'm just going to kind of put these back here. I'll use a highlighter. So, paralysis by analysis, leave that blue. All right. So I have a lot of important information here, but now I got to somehow use this to get at a conclusion. All right. So there's a few things that need to happen here. One is there's some side computations that need to take place. All right. And this is related to the central limit theorem. So the first thing I'm going to do is find a z-score corresponding to these particular values. All right. I said z-score, I meant a t-score because we're dealing with a t distribution. All right. So the t-score, I'll just kind of jot it down up here, t-score is going to be equal to t equals x bar minus mu divided by s divided by the square root of n. All right. So what I did was I took our central limit theorem formula, I put it all together, and I replaced z with a t, and I replaced a sigma with an s. But it's the same formula. All right. Because if you think back, we have the central, I'll just kind of jot it down over here. Our central limit theorem, we had mu sub x bar was equal to mu, and we had sigma sub x bar was equal to sigma over the root of n. And if I wanted to say z equals x bar minus mu sub x bar over sigma sub x bar, I would just pop in these individual values. So it would be, make it a little smaller. So I can replace this with this, and I can replace this with this, just to keep it nice and clean. X bar minus mu over sigma over the square root of n. So all I'm doing here, to make a long story short, too late, I know, is I'm taking the z, replacing it with a t, because it's a t distribution, and I'm replacing the sigma with an s. Z with a t, sigma with an s, but other than that, it's the same formula. All right. So we just have to use that to determine the t-score, and then that will give us a sense of where, what we're up against here, right? So this graph is going to kind of go a long way towards helping us figure that out, right? So buckle up, I guess. Nah, it's really not that bad. It's an acquired taste. It's just weird. And I also kind of regret making the conclusion area like front and center in the workspace there, because I need to write stuff, but it's all the stuff is really happening in the Desmos. So I have t, I'm just kind of write it again here, x bar minus mu over s over the square root of n. So t would be equal to 5.7 minus the mu value, which we're claiming is equal to 5. And honestly, there aren't any other numbers in the problem. What else is it going to be? So that's one of those things where it's like you have a certain number of places to put numbers, and you got a certain number of numbers. So find a home for each of the numbers, and you'll be in pretty good shape. All right. So this would be my t-score. All right, so I just got to crunch that. All right, it's not pretty, but it's doable. So I'll just find an open field in my Desmos. I'll look it up later. I just wanted to make sure that I actually gave you that one, but if not, it'll be there, I promise. 5.7 minus 5 over 2.1 over the square root of 45. So it's about 2.236. All right. So now what I need to do is, well, it's a couple of things. I need to come up with the p-value associated with that. All right. So what that means is that there is a probability associated with this number. We just got to figure out what that is using this graph or one of these graphs. All right. So let me just show you. I'm going to get rid of this so it's a little cleaner. If you go for the areas in the student t distribution, just that first part of it, you know what? It's going to bother me. Sorry, I just got to check. If it's not there, it's kind of important. I mean, more than kind of important. It's just absolutely important. Calculators. Student t distribution calculator. All right, it's there in Blackboard under calculators. All right, so I just wanted to make sure, because I would not feel good about things if it wasn't there. Right. Step 2 is making sure it works, so I'm just double checking that too. All right. Yeah, so you might have to kind of play around with some settings, but it's there. All right. So the calculator technique that you're using, I wrote calculator test here because it's based on the TI-84, old school. Now it's going to be the calculator name, I guess, but whatever. That'll be a typo thing. It's t distribution. All right, so the p-value, pretty simple. The way you're going to get the p-value is by putting in your n value here, And that automatically takes care, and you can use a slider if you want. You know, I don't know why I didn't, honestly. Oh. So slide it to 45. Take your T min, because in this situation, we're looking for a greater than, right? So greater than, if you remember back to our central limit theorem and all that stuff, the normal distribution work that we did, greater than meant to the right of. Right. So I'm looking for the probability, right? So the probability that the T value is more than 2.236. So just kind of looking at this notation here, and I'll just kind of move things along, literally and figuratively. Let me make sure I mumble in myself a lot because that's not weird. So the probability that T is greater than, so the symbol here is going to be consistent with the symbol that we use in the alternative hypothesis, 2.236. I would make my T min 2.236. That one I do have to type in. And the maximum, I just make that something big, something sufficiently big. All right, we talked about that when we were talking about the normal distribution stuff. Big is a relative term when it comes to the normal distributions and central limit theorem. Right, so relative to 0, 10 is very large, right? And in fact, as you slide along, you see that your probability starts leveling off into the point where it doesn't really change too much anymore. You know, some of the values on the back end change, but if you're rounding to 3 significant digits, you got what you need after getting like to 5 or 6, right? So the probability that T is going to be greater than 2.236 is going to be approximately 0.0152. All right, so that number is our p-value. So that value, all this stuff was for the purpose of getting this one number, which now I got to like write super tiny to fit in there. So we have everything we need in order to draw our conclusion. Just kind of weird, you know, because it doesn't look like we do. But it's the relationship between the p-value and the alpha value, right? I didn't write it down before because it wasn't really relevant just yet. Well, I did write it down, but I didn't really kind of emphasize it. It's the relationship between the p-value and the alpha that determines whether or not we reject. So this statement right here, this step 3, if the p-value is less than the alpha value, you reject the null hypothesis. All right, so I'm going to compare the p-value, 0.0152, and I'm going to ask, is that less than 0.01? Put a little question mark above it. All right, that's the question. If it is less than the alpha value, if the p-value is less than the alpha value, then I reject the null hypothesis. It's not. I say a big old no here. So I'd say do not reject the null hypothesis. All right, so I do not reject the null hypothesis, which means if you're not rejecting something, you're keeping it, right? So if I'm just like, where does rejection happen in life? The first thing that pops into mind is like somebody asked somebody out on a date, right? Like somebody asked me out on a date and I don't reject them. I'm going out on the date with them, right? So that's what's happening there. So do not reject the null hypothesis means I'm keeping the null hypothesis. Put a little check mark next to the HO. The alternative hypothesis, if it's a choice between HO and HA, the HO is the keeper, HA is out of there. All right, so we know that the null hypothesis is going to be more true than the alternative hypothesis. All right. So we're defaulting to the 5 minutes in absence of evidence that it's actually more than 5 minutes. All right. It really is the innocent until proven guilty kind of thing, with the alternative having the burden of proof of guilt. So innocent, mu equals 5. Guilty, mu greater than 5. Well, we didn't have enough evidence to say that the individual is guilty, so we default to innocent. Now, are they really innocent? No idea. Can't look inside somebody's heart. Did they really do it? No idea. Hope they didn't. But we don't have enough evidence to say that they did, so they're free to go. All right. So that HO in a hypothesis test is on trial. That's really the key to everything. Once you realize that, then you realize that everything you write in your conclusion is going to be with that in mind. So when I say there is either sufficient evidence or insufficient evidence, the first thing that I'm going to address is the null hypothesis. I'm going to address the person that's on trial. Can you imagine, like a person's on trial and they're reading the verdict and they talk about everything else except for whether or not that person is guilty. Okay, now it's time for the verdict. And you say, well, we don't think he committed the crime. We don't think this, and we don't think that. We don't think that. We don't think that. And then they're like, well, can you actually just tell us if he's innocent or guilty first before you get into all the reasons why you don't think anything? So that's really what's happening here, is that you got to make the statement. You got to say guilty or not guilty. All right. So there is insufficient evidence to reject the claim that the population mean time to leave school is 5 minutes. All right, because the first part is where we state the null hypothesis in words. All right, so population mean, that's the mu. Time to leave school, okay, that's helpful. Is means equals 5, and then of course the units to go along with that. 5 minutes, 5 hours, 5 days, whatever. At the 0.01 significance level. Now we also have to address the consequence of that. What does that mean? It means that he's free to go. No, it means that the claim that it actually took more than 5 minutes has got to be, well, it can't be true. Right? So the claim that the time was more than 5 minutes is false. Right? Oh, that's not a highlighter. All right. So the time that it was more than 5 minutes is going to be false. So, it's like I said, it's an acquired taste. There's a lot going on here. The computations on the side, you'll find that are probably, they'll tend to be the least confusing aspects of these kind of problems. But once you get the hang of it, the conclusion writing, the statements of null and alternative, they're pretty consistent. You'll find that the only work that you're really doing here at all is the computations of the t-score, right? So what I'm going to do is I'm going to do another one of these kind of problems, because I obviously don't want to rush it. I'll do another one like this, and then we'll do, if we have time, we'll do the next concept, but I honestly don't think we will. Let me just see if I have one handy here. If not, then I'll just make up one. Oh, actually,
So quick question, like from a context standpoint, if I was gonna do that, if I was another teacher who was sitting next to that teacher who was measuring everything and another lounger, and she was like, I take time, he or she was like, I time this all is 5.7. And I was like, there's no way that's true, because then I would go through this hypothesis to say that I disagree with this, and here's proof because, is that right? Just like
exactly, Monday.
Okay, all right.
Yep, you got it. All right, so it looks like I'm making one up on the fly, which I can do, because I'm kind of creative when it comes to that kind of stuff. Let me just get a new page here. New blank page. I know. I'll just leave it here for now, and then oh, I don't even know what I just did. Wait, I could have multiple good notes open at the same. I had no idea. It changes everything. I mean, it doesn't, but I like to pretend it does. Huh, that's funny. Anyway, I'm just going to move this over a little bit. So I'm going to say, as a quick side, oh, it didn't really create a new folder. The amount of gas used by a driver on a weekly basis on average is normally distributed a sample of 72 drivers. Is selected at random. Apple Pencil can't keep up with me. And the mean and standard deviation are determined, or I'll say found, to be 12.1 gallons and 2.2 gallons, respectively. I guess I got to get the word "add" in there first. The 0.05 level, significance level. Sometimes we say level rather than significance level for short. So at the 0.05 significance level, test the claim that the population mean amount of gas is less than 15 gallons. All right, so yeah, I wrote that like jumbo, like shrink it down a smidge. This will all be posted in the same note packet. It'll be there for you. But the amount of gas used by a driver on a weekly basis, on average, is normally distributed. Sample of 72 drivers is selected at random. And so that initial driver is considered the basis, it's considered to be an exemplar of drivers, so that's the generalization. A sample of 72 drivers is selected at random, and the mean and standard deviation are found to be 12.1 gallons and 2.2 gallons respectively. So that means the 12.1 goes with the mean, 2.2 goes with the standard deviation. At the 0.05 significance level, test the claim that the population mean amount of gas is less than 15 gallons. I'm actually surprised I was able to say all that without coughing up a lung. So, a little throat clearing though. So what we would do to get started here first is get all of our statistical information. A sample of 72 drivers. So N is 72. The mean. I have a different color here. The mean is 12.1. So that's the mean for those 72 drivers. With a standard deviation of 2.2. I'm not really concerned about the units because they're consistent. The units are gallons throughout, so I'm not worried about that. For things like that, I mean, it would be kind of mean for me to be like 12.1 gallons and 2.2 quarts or something like that. That would be just, that doesn't do anything it doesn't add anything to the conversation. So you don't have to worry about that, right? Also the alpha value. So just make a note of that. Alpha value is given to be 0.05. Okay, so the first thing, once we've identified all that information here, is test the claim. So we want to state our null and alternative hypotheses. Test the claim that the population mean amount of gas is less than 15 gallons. All right. So just think about what we did before. Well, our possibilities, using that benchmark, 15 gallons, well, our population mean could be equal to 15. It could be more than 15. It could be less than 15. It could just simply not be equal to 15. That's just in general, having nothing to do with this problem. Right? That number is 15. We're talking about a population mean. Those are some possibilities. Now, from that, we pick the two that make the most sense based off the problem. Right? So I'm just going to kind of chuck those over here because I need to come up with the null, HO, and the alternative, HA. The null always involves the expression, the equation with an equal sign. Well, really the equation, right? Because that's the only one that has an equal sign. All right, so mu equals 15, that's going in as my null hypothesis. All right. Now, out of the possible alternatives, all right, so these are my possible alternatives. The one that's consistent with the question, less than. That's the one that I'm putting in as the alternative hypothesis. And you know what? I'll just copy it. Oh, almost. So now I have my null and alternative hypotheses established. Try to make it like flowchart like. I have to do a couple other things. I gotta get my alpha value, which I already know. I need to get a p value. That p value is going to come from the computations that we're about to perform, right? But again, Desmos is going to do the work for us, so it's not like we're not going to lose any sleep over that. But the thing is, if you're taking a long time to really buy into this whole Desmos thing, then it's like, well, there's a little bit of a learning curve, but you're going to have to make it a point at some point, right? So we need the t value, the t score, So again, t is equal to x bar minus mu over s over the square root of n. All that information is stuff that we know. All right, so t is equal to 12.1 minus the assumed value for mu, so 15. All right, so this value here is always going to be the assumed in HO, or quality H. Not much better, but whatever. Over S, which is 2.2, over the square root of 72. So that stuff goes into Desmos. 12.1 minus 15, new fraction 2.2 divided by the square root of 72. That's a astronomically small value. So t is going to be about, I'll use the approximate symbol, but we're going to round it anyway. Negative 11.185. Now, because the alternative hypothesis is a less than symbol, I'm going to find the probability that t is less than that number. All right. So that goes right back up into the early part of the computation. The one thing that people are always going to have to, become comfortable navigating is the sliders. Because I've had people, even people who are somewhat experienced with Desmos, being like, the slider only goes up to 50, but I need to go up to 72 here. Well, yeah, just type on it, a 70, tap on it, type a 72, and then just move on. If I want it to be on the high end, a negative 11.185, I'll just kind of move this up a little bit. What we're talking about here, and I'll just quickly draw a diagram just so you get a decent visual. Zero's in the middle, negative 11, I'm just going to kind of estimate as being around right here. It's not, but much further. But if you're out here at negative 11 and you want to be less than that, you're talking about all this stuff on the fringe here, right? So you want to be something substantially less than negative 11, right? So something less than that. I mean, ideally negative infinity, but something much less than negative 11.185 on the low bound. All right. So my T min, like negative 10 is not going to do it. I could slide all the way to negative 10, but if I put in my T max, negative 11.185, then it kicks back an error on my cumulative probability computation. Right? That's no good. But that's because your minimum can't be larger than your maximum. It doesn't make sense. Right? So I need this number to be much smaller. So I just tap on it. I can do it one of two ways, actually. I could tap on the number and just make it something smaller, like negative 20. Or I can tap on the T min, the left bound, and make that something really small, like let's say negative 50. And then when I go back into the slider, you see that now the slider allows me to go further. It's up to you which way you want to go. But, some people are just more comfortable tapping on the number and just changing it. So let's say you make it negative 20. And then you look at the number and say, okay, well, let me make it negative 25. Okay, no change. That's really all you're looking for. You need something that's going to be substantially small compared to the number that you're referencing. All right. So the number here that's on the high end is negative 11.185. Whatever I put in as T min has to be much less than that. All right. So you want to play it safe, put in like negative 1,000. right? That'll do the job. You know, just go nuts. Just go way less and call it a day. You know, either way. Regardless, you get a probability value of 1.272. Right, that's not the final answer. I just got to move it over a little bit. Times 10 to the negative 17th power. All right, so that's like saying 0.00000000000000001272. All right, that's just, I mean, that's damn near zero. All right, so 1 point, oh, I can actually probably give it a little bit bigger. So 1.272 times 10 to the negative 17th power. All right, that number gets compared to the alpha value. All right, so we make a determination. We can just kind of chuck this diagram in over here. All right, so we want to know, is the p value less than the alpha value? Is p less than alpha? So is (1.272) times 10 to the negative 17th power less than 0.05? And the answer is yeah, it is. A lot less. One of them's exactly 5%, and the other one is close to zero. Right? Just doesn't seem like, when you get into decimals, it doesn't seem like there's much of a difference, but there's massive difference there. So that allows me to reject the null hypothesis. I'm just going to make this a little bit nicer. All right, so therefore, we reject the null hypothesis. All right. And actually, let me throw a yes in there. So if we're rejecting the null asked me out on a date and I rejected it. Get out of here, null. I don't like you. That means that my choice is the alternative. What's my alternative? I don't know, anything but the null. So I can now conclude that the alternative hypothesis is the one that's true. All right. So when we write our conclusion, we follow the template. But that's kind of like, that's the finish line. You know, once you get to that, it's like, oh, this is great. You know, like I've finished the challenge, but you know, I got to say that most people who screw this up, they screw it up in the conclusion. They don't screw it up, believe it or not, because some of this looks really complicated. They don't screw it up until they get to the conclusion. Right? So you had a choice of insufficient or sufficient evidence to reject the null hypothesis. Well, we're rejecting the null hypothesis, so there is sufficient evidence to reject the claim that the population mean amount of gas first sentence always addresses the null hypothesis. That involves an equal sign. So is 15 gallons at the 0.05 significance level. All right, so that addresses the first part, but I still haven't answered the question. All right, so we've addressed guilt versus innocence. So we just pronounced the defendant guilty. Now we have to deliver the sentence, like sentences in prison sentence. So therefore, the claim that it, because we know it now represents the population mean amount of gas, so we can say it is less than 15 gallons that's going to be true. And that has to do with the fact that I selected the alternative hypothesis. All right. That alternative hypothesis is addressed in the second sentence. And we indicated by rejecting the null hypothesis that it's the alternative hypothesis that's true. All right. So it's really weird stuff. And I always, honestly, without much exaggeration here, I always kind of feel bad teaching this material because I know that it kind of produces anger in lots of people because they look at it and say, what the hell is this? And why are you doing this? This is, honestly, this is the best case scenario, unfortunately. Because you saw that there's 5 different hypothesis tests. We're only going to do 2 of them. But but this, this is really important stuff. I mean, that's kind of like why we're here. We evaluated samples, we evaluated populations. The only thing that's left is bridging the gap between the sample and the population. So it kind of makes sense that we would eventually have to do something pretty heavy, and so this is the heavy, right? So, we'll do more examples with this on Monday, and as part of the review. So so just stay tuned for that. The one thing I got to tell you is that the review that's posted, because I kind of trimmed a lot of the fat in the course, the review that's posted is going to end up, or it does contain a lot more than you would be responsible for on the unit test. So so look for a revised version of that tomorrow. Right, I'm still in the process of putting the finishing touches on that. All right, so let me check the chat. Yeah, exactly. So yeah, anyway, with that, I think I've kind of preached at you enough for the evening, coughed at you enough. Fortunately, there's a screen separating us, so unless whatever I have can travel through a computer system, I think we're all safe. Well, you are. So anyway, at this point, I would say let's call it a night. Enjoy the rest of your evening, and again, be on the lookout for that updated review problem set. I'll send out an announcement tomorrow when it's available. So enjoy the rest of your evenings, and I will see you all Monday.
All right. Thanks.
You're welcome. Take care. Will do, Ginger. Will do. Just got to go to the store and get some.